Okay, good morning, everyone. Welcome back to class. Let's get started here. It's the 10th of October. So yeah, we're working our way through chapter 4 here, about halfway through. So let's see. Next week, next Thursday, we'll have fall break. And then week and a half or so after that, we'll have exam 3. So still a little bit off in the distance there, exam 3. It'll cover chapter 4. And so, yeah, are there any questions? Anything you guys want to talk about? Anything from last time? So this is where we were at last time. we, we're here in chapter 4 and we're talking about quantitative data, right? So chapter 3 was categorical data and chapter 4 is quantitative. And so the two chapters have a similar kind of path. We begin with statistics, tables, graphs, and then we move into inference, into confidence intervals and hypothesis testing. So that's basically our track for chapter 4 as well. So we've been talking about statistics. So what are these statistics we've been talking about? Well, we have measures of center. So that's mean, median, mode. Okay, and then we have measures of spread. There's our old friend, the standard deviation, but we also have interquartile range, and we'll add a couple more today as well. So these are numbers that describe data sets, so they're statistics. We've added in several graphs. Last time we did the box plot. So we're basically doing what's called descriptive statistics. We're learning how to describe data, and that's very important. A lot of important work is done with descriptive statistics. So that's where we're at. We're almost done with describing, and we're going to move into the inference side where we start building confidence intervals. But first we have to know how to describe. Okay, so we're done with the center, measures of center. We're right here in measures of spread. So we know standard deviation. We learned about the IQR. And so if we continue on in our lecture notes here on page 117, we'll talk about measures of variability. Okay, so variability we know is related to consistency. So they're inversely related. So if variability is high, then consistency is low, and vice versa, right? So in many things we value consistency, right? There's some things where we like to have variability and novelty, but in a lot of things we want consistency. So when you're working with stuff where consistency is important, we need to have a way of measuring that consistency. So we measure the opposite, which is variability. Okay. All right. So what are some of these common measures of variability? One is the range, and the range is pretty much what it sounds like. You take the maximum value in the data set and you subtract the minimum and you get the range. So that means in this small data set here, it ranges over 4 different values or 4 units. Okay, and it's very easy to compute, but it does have some significant flaws. It does not use most of the data, right? It ignores almost all of the data. Okay, and it's entirely dependent on extreme values. So it's about as not resistant as you can be, right? It's going to be, it's based on, any outliers, any extreme values you have. So it changes quite a bit, if you have outliers. So it's not resistant to outliers at all. But that said, it's easy to compute and it does give us information. So we compute it. The way it works in industry is you use software. And so software can calculate all of these statistics very quickly. So we calculate all of them, and then we use them, and we give more weight or less weight to some. So anyway, that's the range. So that's a common way of measuring variability. The other way is another way is the standard deviation. So in chapter 3, we talked about standard deviation. We defined it geometrically in that chapter. So we had a geometric definition for standard deviation. So if you remember, we said we have the mean in the middle, we have an inflection point over here, and then there's a distance from the middle to the inflection point. Okay, and that distance is the standard deviation. That's a geometric definition. It's a perfectly fine definition for standard deviation, but there is a formula as well, especially when it comes to quantitative data, which is what we're doing in chapter 4. So there's actually two formulas. Okay, there's the population standard deviation and there's the sample standard deviation. And that's because we have samples and populations, right? So if you do have the entire data set for the entire population, then the standard deviation is given by this formula. So we divide by the whole population size. If you're working with a sample, and most of the time we're working with samples, then the formula is given by this. Okay, so so there's two different formulas. They're basically very similar, although they do differ in one way that might surprise you. So let's look at this formula a little bit deeper here. So inside we have x minus the mean. Okay, so what we do is we take each data value and find its distance from the mean. Okay, then we add those up. That's what sigma tells us. I'm sorry, we take each of those distances, we square them, and then we add them all up. Okay, so we have the sum of the squared distances. Then we divide by n, and what that does is it gives us an idea of the average squared distance from the middle. Okay, and then to get rid of the squares, we take the square root. Okay, so it's basically giving us the average distance away from the middle of the data set. Okay, so it's called the standard deviation. And before we defined this geometrically, but now we're defining it with a formula. This is also good. It's also progress. Okay, so what are the advantages? Well, it has a good interpretation. It's basically the average distance away from the middle of the data set. And it's measured in the same units as the original data. Okay, so if your data set is in hours or in pounds, then your standard deviation will be in the same units, hours or pounds. So it has a really nice and easy interpretation. It also uses all of the data. So those are the advantages. The disadvantages are that it's not resistant. It's actually quite sensitive to outliers and to skew. So if you have outliers, if you have skew, standard deviation might not be the best one to use. And this is a little bit strange. This is might seem like a weird idea to you, but it's actually a little bit biased in its estimate of sigma. Okay, so the sample standard deviation is actually a little bit off over time. Okay, let me skip the variance for now, and then we'll come down to the interquartile range. Oh, sorry, I forgot to mention one thing. On the standard deviation, notice that the denominator here is different than the denominator here. So the sample standard deviation formula will give you a different number than if you're working with a population standard deviation formula. So when you're doing analysis, it's very relevant. If you're, you need to know if you're working with a population or a sample because it'll give you different numbers. Okay, so just keep that in mind. We're going to do some examples in a little bit. Okay, then skipping the variance for just a minute, let's come down here to the interquartile range. This is the one we talked about last time. Okay, so the IQR is Q3 minus Q1. Okay, so, and if you remember, the quartiles themselves are like medians, right? They're medians of the upper half and the lower half of the data set. So since the IQR is made up of medians, it's not affected by outliers or skew. Okay, so we say that it is a resistance statistic, so it's good. Its weaknesses, it only uses the middle 50% of the data, right? Q3 is a 75th percentile, Q1 is a 25th percentile. So Q1 and Q3 are based entirely on that middle 50% of the data. Okay, and then finally, it doesn't really give any indication of whether or not some data values are more clustered together. Okay, so these are all ones I think make sense. We talked about interquartile range. The range is quite basic. Standard deviation, this is a little bit new and old. I mean, we've talked about standard deviation before. We never really had formulas for it before, so there's some new stuff there. And the other thing that's a little bit new and maybe a little bit weird is how we have two different formulas, one for the population and one for the sample, and the denominators are slightly different. Okay. Do you need to memorize those formulas? No, they're here on your formula card. So they're right here. Okay. And not only do you not have to memorize them, I'm going to go a step further and tell you you don't even need to use them really. Okay, I want you to see them and be aware of the formulas, but for our intro stats class, we're not really going to be using them by hand. You'll use software to calculate these rather than by hand. So you don't need to calculate the standard deviation by hand in this class. You can just use software for that. Okay, so if we, everything we decide to put in or take out of this class is kind of a trade-off. So if we were to make you do these by hand, then it would take up class time and that would prevent us from doing other things, right? So we decided we'll downplay the importance of calculating these by hand, save us some time, and we'll add in some other topics later, okay? So you don't need to basically use these formulas at all. I want you to be aware of them and to see them. But when it comes to standard deviation on homework and on exams, you can use the software for that, okay? So just keep that in mind. Don't spend an hour trying to get this formula to work by hand in the homework, okay? Just go right into GeoGebra, as I'll show you in a second, to calculate those, okay? So good. So the other one here is the variance, and the variance is simply the square of the standard deviation. Why do we do that? Well, what happens when you square a square root? When you square a square root, the square root goes away, right? So it basically allows us to not have to work with the square root function, and that's nice. Because square roots are slightly complicated, right? And there's plenty of complicated stuff in this class already. So let's practice with calculating some of these measures of variability. Okay, so we'll do a mixture of by hand and with computers and calculators here. So let's practice with min, with the range, standard deviation, and IQR. And so we'll pick this data set here. So let's say this is a sample of 10 college students. Okay, and so that's relevant. This is not a population, this is a sample. Okay, so n is 10. And every student is going to have some number of hours they spend working, right? So at a job, right? So you could be spending 0 hours at a job, right? Or you could be working full-time or even more. But in this particular data set, the smallest was 0 and the largest was 40. So nobody was like working overtime in here, okay? So so what would the range be? If we're trying to measure how spread out number of hours worked is, we could start with the range, right? So the range, remember, is max minus the min. Okay, so the max here is 40, the min is 0, 40 hours for the range. Okay, so that's how spread out this data set is, right? It ranges all the way from 0 up to 40. What about the standard deviation? Okay, so there's two formulas for the standard deviation. Okay. There's the one for the sample, and then there's the one for the population. So which one would we use if we were going to do this by hand? We would use this one right here. Okay. So again, what it tells you is it finds each value's distance from the middle, xi minus x bar, then it squares that distance and adds them all up. Okay, so we have the sum of the squared distances, then we divide by the n minus 1, so it gives us kind of an idea of the average squared distance, and then we take the square root of that. So it's basically a measure of your average distance from the middle of the data set. Okay, but we're not actually going to calculate that with the formula. We're going to use software. Right? If you want to do that by hand, be my guest, but you're looking at a lot of time dedicated to that, whereas we want to talk about other things as well. So we're just going to use software for the standard deviation. Okay, so we'll go sigma, we'll hit the toggle button, then we go 3 dots, and I need to get the data set into GeoGebra, right? So we open up the spreadsheet, and we're going to type those numbers in. Okay, so again, I'm just typing in the numbers from this data set. Okay, so I'll start here in A. If you want to do this along with me, great. If it's too difficult on one screen to do all of this at once, you can just watch, and we've got videos for all of this, right? So you can go back later and watch videos if you'd like. So we'll highlight the data, and then we hit the histogram. And this is one variable analysis because you can only have one number of hours that you work in a week, right? And so we get our histogram there. We can just remind ourselves we could do box plots, we could do stem and leaf plots, we could do dot plots, right? It's very easy once it's in the software. But what we're talking about here is variability. So I'm going to hit the sigma x because so many formulas have sigma in them. That sigma x is just saying, hey, this is where you go to get all of your statistics, all of your numerical summaries of the data. Okay, so this will tell us the standard deviation. But there's 2 standard deviations. There's sigma, which is the population standard deviation, and then there's S, the sample standard deviation. Okay, and because those 2 formulas are different, they give you slightly different numbers, right? Again, if we go back to the formulas, they're slightly different. Okay, the population standard deviation divides by capital N, whereas the sample standard deviation divides by n minus the sample size minus 1. So which one do we use? Well, what do we have? Do we have a population or a sample here? It's a sample, right? So it's really easy for students to mess this up because they see sigma and they remember, well, that's standard deviation. But there's 2 standard deviations. There's the sample standard deviation and there's the population standard deviation. Okay, so S is actually what we want here, 12.6 repeating. Okay, so S equals 12.6 repeating. So maybe we'll round that to the 2nd decimal place. And again, one of the strengths of the standard deviation is that the units are the same as the data. So this will be 12.67 hours. And what does that tell you? Well, it's a measure of the typical distance from the middle of the data set. Okay, so the typical person is within about 13 hours of the average number of hours worked. Okay, so it's basically a number that tells you how spread out the data are. Okay, all right, IQR. IQR, remember, is the so the distance between the quartiles. Which quartiles? Q1 and Q3. And it's a range. So it's telling you the distance between those two quartiles. It's another measure of spread. Okay, so how do we get that? Well, I showed you how to do that by hand, but we can also do that with GeoGebra, right? So we have 30 and we have 18. So 30 minus 18 is our IQR. Okay, so we'll go 30 minus 18 is 12 hours. Notice that that's, consistent. It's not exactly the same, but it's consistent with our standard deviation measure of spread. Okay, so those aren't expected to be the same value. In fact, it'd be almost surprising if they were exactly the same. Okay, but they are, roughly this, very similar kind of picture, right? They're telling us how spread out the data are there. Okay. All right, now variance, remember, is the square of the standard deviation. Okay, so for the variance, we're going to square the standard deviation. Okay, so 12.67 hours, and then we square that. Okay, so if we do that part on the calculator, so we have 12.67 squared, looking at about 160.53. So 160.53. And the units on this are kind of weird. They're in square hours. So, so just between you and me, I'm not going to test you on the variance. It's important, but not really for our class. So so when we put this course together, about half of us didn't even want to have the variance in the course. The other half said, well, they might need it for another future stats class. So let's just put it in there, let them see that word and the formula for it. But I'm not going to test you on the variance. Okay, so, but it is another possible measure of spread in the data. Okay, let's change this scenario slightly. Let's go from a sample to a population. So, when you're learning about topics, sometimes you do that, right? You imagine a slightly different scenario and you think about the consequences of that, right? So what's our scenario now? Instead of this being a sample of 10 students, let's say that this represents all the students who work at a particular office, right? So let's say these are all of the interns, the student interns at a particular company, something like that, okay? So it's no longer a sample, it's actually a small population. Populations often are large, but they can be quite small. I mean, you could have the population of everybody in one family, or it could be the population of all the students in this Zoom meeting right now. And so, yeah, populations don't necessarily have to be large. This could be all of the students, all of the student interns at a particular office at a company, for example. Okay, so what would that mean for our measures of spread? Well, some of them wouldn't matter at all. Some of them wouldn't change at all. The range is still going to be 40 minus 0, which is 40 hours. The IQR is still 30 minus 18 equals 12 hours. So those two aren't going to be affected, but standard deviation will be affected. Okay, and this is why you have to be aware of what you're working with. Are you working with a population or a sample? So you'll see this over and over in the homework. You'll go to calculate standard deviation. You get into GeoGebra, you get the number, and then it marks it wrong. And it's because you've chosen the wrong standard deviation. Okay, so in the previous example, we worked with the sample standard deviation. Okay, it has a different denominator than when you're working with the population standard deviation. Okay, so since we're working with a hypothetical population here, then the denominator changes and the value of the standard deviation changes. I think you can probably tell what happens. It's a little bit larger than n minus 1, so it's going to be a smaller standard deviation. Okay, and so it's already here in GeoGebra for us. GeoGebra doesn't know if you have put in a sample or a small population. So what it does is it uses both formulas and it calculates this population standard deviation, sample standard deviation, and then it lets you choose for yourself which one is the relevant one. So since this is now a population, we're going to use sigma, so 12.02. Okay. So the standard deviation now is sigma, because this is a population, and it's 12.02. And again, the interpretation is nice. It's still in hours. So it's not like drastically different than the sample standard deviation, but it is different. And so just be aware of what kind of data you're working with. The variance is still the square of the standard deviation. So since we're working with the population standard deviation, the variance will be the population variance. And so we'll still take the square of sigma. Okay, so 12.02 squared. So that's going to be 144.4 square hours. Okay, so again, variance is got an awkward interpretation, but you can think of it as a number that quantifies how spread out the data are. Okay, and like I said before, I won't test you on variance. You might not even see it in the homework. Okay, so it's just something we wanted to mention to you guys for those who take more stats classes. Okay, all right, in the future. So any questions there about that? We're sort of done now with our describing quantitative data. We're done with the descriptive statistics, and we're ready now to move into inferential statistics. But let me just see if there's any questions with any of those problems that we've done. Okay, so as I mentioned earlier, these two chapters are parallel to each other, right? We have the chapter 3, we have the chapter 4. This is categorical. This is quantitative. Okay, so in chapter 4, we developed graphs, right? Okay, so we have stem and leaf plots, we have dot plots, we have histograms. Well, in chapter 3, we had graphs too. We had bar plots, pie charts, etc., right? In chapter 4, we have statistics like mean, median, mode, IQRs. Well, in chapter 3, we had statistics too, right? We had p hat, etc., right? So there were, very similar kind of development. Then in chapter 3, we also had confidence intervals. Okay, so remember the formula for the confidence interval it was the point estimate plus or minus z star times the standard error, right? So it's p hat 1 minus p hat over n. So that was our formula for confidence intervals. We want to do the same thing with quantitative data. Okay, you might be interested in public health, so you would want to maybe estimate the average weight for adult females in Utah or something like that, right? So weight is quantitative. It's not categorical, right? So we need confidence intervals to do that, but the formulas are different, okay? So, so how does it work? Let me write down the formula, and then we'll talk about it. Okay, so it's similar and it's different. Okay, so what are the similarities? Well, we need a point estimate. Okay, so with estimating the population proportion, we used p hat, right, the sample proportion. So if we're going to estimate the population mean, we'll use the sample mean. Okay, so it's basically a point estimate in the middle, plus or minus a margin of error, right? So the margin of error for p hat, for p looked like this, right? We had a critical z-score times a standard error, right? And for x bar, it's similar. It's critical score, but it's a t-score instead of a z-score. And then the formula for the standard error is actually a little bit easier. Okay, it's S, the sample standard deviation divided by the square root of n. So it's very similar in spirit, okay? Kind of similar structure, similar idea, margin of error. But because the data structure is different, right, it does change the formulas a fair amount. Okay, so what we're going to talk about now is the sampling distribution for x bar. Okay, remember back in chapter 3, this formula came from the sampling distribution for p hat, right? We spent a lot of time talking about the sampling distribution for p hat and how p hat bounces around. We said it's normally distributed if certain conditions are met. We'll see a very similar thing here for x bar. We'll see that when you have sample means, they also bounce around, and if certain conditions are met, they can also bounce around in the normal distribution. Okay, so there's a couple of key differences, but from a high level view, they're actually kind of similar. Okay, so let me just show you the formula here. Where is it? It's right here. Okay, so it's the one sample t confidence interval for the mean. We're not quite ready to use this formula, but I just want to point out where we're headed. Just like we had confidence intervals for the population proportion, we want to have confidence intervals for the population mean. Okay, we'd like to estimate the average height for people in Utah, or people in the U.S. or something, right? So we use a very similar thing, this confidence interval. So just like we had to understand the properties of p hat to get the confidence interval in chapter 3, we're going to have to understand the properties of x bar and its sampling distribution to be able to understand the confidence interval formulas. Okay, so that's where we're headed. Okay, and maybe by the end of class we'll do one of these. It'll probably be next week though before we actually use that formula. So let's jump right into the sampling distribution for x bar. Okay, so all of these confidence intervals are based on samples, the sample mean, so we need to understand how that sample mean works. Well, the sample mean will also vary from sample to sample. So that variation, that spread, is the standard error for x bar. Okay, and its value is it's sigma divided by the square root of n. Okay, so you can think of this as the standard deviation for the sampling distribution of x bar. Now, there's a bit of a problem. We don't know what sigma is because, if you're doing inference about the mean, then that means you probably don't know the mean, right? And if you don't know the mean, how do you get sigma? So our way out of that problem is to estimate sigma. Okay, so the population standard deviation gets estimated by the sample standard deviation. Okay, so we say that the standard error is approximately the sample standard deviation divided by the square root of n. Okay, all right. Now, x bar, it turns out, can be normally distributed, but when we estimate sigma with s, it actually takes us out of the normal distribution, and we end up in a new distribution called the t distribution. Okay, and so we're going to talk about the t distribution too. I don't want to talk about it right now, but just want to mention it. So we have a new distribution here in chapter 4. So it's actually a good thing. It gives us more flexibility, but we do have to learn some new properties here for this new distribution. The good news is that it's very similar to the normal in a lot of ways. So it's a bell-shaped curve, and the process will be pretty similar to working with the normal distribution. Okay, all right. So what was the idea that we learned about that told us that p hat would be normally distributed, right? So we talked a lot about this, right? We said, okay, if you look at all of the possible p hat values, okay, you get what's called the sampling distribution for p hat, and it's basically bouncing around in a normal distribution. Okay, do you remember the name of that theorem? It was called the central limit theorem. Okay, we studied it. I think it was way back on page 93. Let me just remind you guys of that. I don't want to bounce around too much in the lecture notes. It can cause some fatigue, but we talked about this back on page 93, right? The conditions for when the sampling distribution is approximately normal. It was based on the central limit theorem, okay? And if we go way back to the beginning of chapter 3, again, I apologize for all of the bouncing around here, but just do it real quick. I just want to show you those words again and just prove to you that we did talk about the central limit theorem. Where did it go? Here it is, right? So way back at the beginning of chapter 3, 40 pages ago, we talked about the central limit theorem, right? So it said the sample proportion will approximately follow a bell-shaped curve called the normal distribution, right, if certain conditions are met. Well, we're returning to the central limit theorem, but not for categorical data, but for quantitative data. Okay, so it's the same theorem, but amazingly, it applies also to sample means. So it applies to sample proportions, p hats. It also applies to sample means, x bars. Okay, so what does it mean? What does it tell us? Well, when you find the sample mean, you're using a data set, right? So you draw the data values from the population. That population will have a distribution. Okay, so it turns out that any distribution will work if you have large enough samples. So we're going to draw our data values from a population. We call that the parent population. Okay, and if certain conditions are met, then the sampling distribution of X bar will also be bell-shaped. Okay, just like the sampling distribution for p hat will be bell-shaped. Okay, what are the conditions? Well, either the underlying population is normal or the sample size is large enough. Okay, so it's actually pretty basic. Either the underlying distribution is already normal or you have a large enough sample. The rule of thumb is 30. In other words, as long as you have a sample size of 30 or more, the sampling distribution will be normally distributed. Okay, so let's try to make this a little bit more concrete. We're going to do a class activity here, and we're going to roll some dice. We've been flipping a lot of coins in here. This time we'll roll die. Dice, and the reason why is because when you roll a die, you get a number between 1 and 6, right? And so it's more like quantitative data, whereas flipping coins, it's more categorical, right? So we're still doing gambling, don't worry. But now instead of flipping coins, we're going to be rolling dice. So I need you guys to pull out some dice. Okay, so if you don't have any dice with you, you're going to need some virtual dice. Okay, so there's tons of websites that do this. So probably the best one would be rolladie.net. Okay, so if you can go to this website here, you can do it on your phone or just open up another window in your browser. And I'm going to need everybody to participate. We have 10 people here, so we should be able to get a pretty nice data set going. It takes a little while, but I think it's worth it. I think this is a nice activity, and we do, I think, see this central limit theorem pattern appear if we do it correctly. Okay, so what do I need you to do? I need you to roll a single die and tell me the value. Okay, don't do it yet. Let me just demonstrate. Okay, so here's the scenario. We want to estimate the average roll of a die. Okay, so let's estimate the average roll of a die. Okay, well, why do we need to estimate it? Don't we know it? Yeah, and that's kind of the beauty of using dice. We already know the answer right before we begin, so it's kind of nice. We can actually estimate it using a sample, and then we know where it's headed, sort of thing, right? So what is the average roll of a die? Well, when you roll a die, it can be a 1, 2, 3, 4, 5, or 6. And they're all equally likely. So what is the middle of that distribution? It should be 3.5, right? I mean, if you sat there and rolled a die all day long, and so first you get 2, then you get 4, then you get 1, then you get 6, right? If you add up all those numbers and you divide by the total number of rolls, you'd expect about 3.5. That's the middle of the distribution, right? So we actually know the answer. It's like we look in the back of the book, right? And we actually know the answer before we get started, right? We know that mu is 3.5. But let's say we couldn't look in the back of the book. Let's say we'd never worked with a die before, and we wanted to estimate it using a sample, right? What would we do? Well, let's roll some dice and see what happens, right? So I need everybody to roll the die a certain number of times. So let's do this 3 different times with varying sample sizes. Okay, so each time we'll have a different sample size. And again, the central limit theorem says as the sample size gets larger, the sampling distribution becomes normally distributed, right? So we'll start with a very small sample, the smallest, 1, and then we'll get to larger. Now, 3 is still very small, but at least it'll change from one to the next. Okay, so if I have a sample of size 1, then I'm just rolling a single die, right? So let me show you what happens here. So I'm going to hit go, and I got a 6. Okay, so I've got a dot over here, and I'm going to do it twice. I think if we have everybody do this twice, it'll be better results. So now I've got a 4, and there's my second dot. Okay, and we're off. So everybody roll that die twice, or you can roll 2 dice once, whatever you want, and put the 2 numbers in the chat for me. Okay, so everybody should have 2 numbers. For example, I have a 4 and I have a 6 like this. So just put your numbers in there. I'll give you guys about 30 seconds to do this. And just keep those numbers coming in. And as you're doing that, let me just again remind you what we're doing. We're taking a sample of size 1. So when I roll my die 1 time, my first X bar is 6 divided by 1. It's 6, right? So that was my first X bar. Then my second X bar, I got a 4. So I add up all my numbers. It's just 4. Divide by the sample size 1, and I get 4, right? So those are my 2 X bars. And they're allowing us to start to estimate what the average roll is, right? We know it's 3.5, but that's where we're headed. Okay, so it looks like the numbers are done coming in here. So let's put these in. So Killian got a 3 and a 5. So those were his 2 X bars there. Then Crystal has a 1 and a 2. Polly 4 and 1. And we have a 3 and a 5. Armand has a 4 and a 5. And we've got a 2 and a 4. Are we seeing any clear pattern here? No. We did get a lot of 4s, but let's see, is that the last one? And then we have a 2 and a 6. But it would be weird if like everyone had the same exact amount, because we should have some probability going on here, right? Some randomness. So what kind of distribution is this? This is actually a uniform distribution. Okay, so we're drawing our X bars from a uniform distribution. Okay, so the middle, the average, is actually the balancing point for our histogram, for our dot plot here. And so if you imagine balancing this board of dots, I think actually 3.5 looks pretty good for the average, right? For the balancing point there. And so yeah, that's basically in agreement with what we said earlier. The middle should be about 3.5. And that certainly looks like about where we would balance. Maybe a little bit higher, a little bit lower, but that's just because we have a fairly small sample size here. Okay, so let's make the samples a little bit bigger, right? So now we're gonna roll 2 dice. Okay, so go back to the website and let's see. I think I can just do 2 here. So I'm gonna go 2, and again, just watch really carefully. We don't wanna get anything messed up here. So now I'm gonna roll 2 dice. I have a 7. Okay, so my first X bar is, what was it? It was 2 plus 5, right? So I have 2 plus 5 divided by 2, because I have 2 in there. So that's 7 divided by 2, that's 3.5. So my first x bar is 3.5. Okay, let me do it again. So I'll have my second x bar. And again, what we're trying to do is trying to understand the average roll of a die, right? So, and interestingly, I got another 7. Okay, so that's 7 divided by 2. So I have 2 x bars that ended up being the same exact value. Okay, so I want you to do the same thing and then put in your 2 numbers in the chat, just like I did right there, right? I have a 3.5 and then my second was 3.5. So again, back to it. Shouldn't take too long, really. If you use the applet correctly, just 2 clicks of the button there. And oh, you might have to divide by 2, yeah, with your calculator, but it shouldn't take too long. Does this make sense to everybody? If you didn't catch any of that, no shame. Just tell me, and I'll go through the directions again. And once you have your numbers, put them in the chat over there, and we're going to see if we can get this this behavior going. Pabrita, I think you've got the wrong denominator there. 4.3, I don't think that's a possible number there, because the dot plot here has all of the possible values. If you have 2 numbers ranging from 1 to 6, and then you add them and divide by 2, it should be one of the numbers given here on the number line. So does that make sense? So if you could redo that and give me your numbers again, that would be great. I'd like to have everybody's numbers here. Everybody is helping quite a bit here. So, all right, I'm going to start putting these in. So Killian. Okay, so were there any other numbers that were going to come in here? Caprita, did you get your numbers? So, okay, what happened? Oh, 2 and 3, perfect, thank you. Do we see any sort of pattern forming here? Well, okay, if we had to balance this, where would you put that balance point? Maybe about right there, pretty close to 3.5 again, maybe a little bit to the left, but it's not really clear. I'm just kind of eyeballing it, right? So it looks like the center is about the same. What about the spread? I think it's obvious that the second has less spread in it, doesn't it? You know, there's no values at the extreme ends, right? Nobody got 2 6s, nobody got 2 1s. The data is, the data are more, compact here in the middle. And I might be reading too much into this because I know what it's supposed to be, and so maybe I'm just biased here, but I do kind of feel like there's a mound that's forming there in the middle. So maybe I'm reading too much into that though. So let's not get too excited. Okay, but definitely the center is in the same or similar place, and there's less spread. I think you guys all agree that there's less spread there. Okay, all right, let's do one more. This time we're going to do a larger sample, and if you're doing real samples, then you wouldn't do 1 or 2 or 3. You would do like 30 or 300 or 3,000, right? But for the sake of class, we can't do that many really. So I'm going to do 3 now. So I'm going to go roll 3 times. And so I get 3 die. I have a 1, a 5, and an 8. Okay, so it's getting a little bit more involved with the arithmetic. So I have a 1, a 5, and a 3. And now I'm going to divide by 3 because my sample size is 3, right? So that's 9 divided by 3. So I believe that's a 3, right? So I have my dot there. That's my first X bar. Okay, and then For my second X bar, let me do that again. So I'm gonna hit go one more time. Now I have 6, 1, and 2. So 6, 1, 2. So 6 plus 1 plus 2, divide by 3 because we did 3, so that's 7, 8, 9. So interestingly, I got the same again, but you know, it's not surprising that that would happen. So there are my two dots. Guys, get to work here. Give me more dots here. So again, over in the chat, I would put a 3 and a 3. Okay, so if you can go ahead and do that. You guys are quick. I think you even got yours in before I got mine in. So good. So Crystal, I think you were the first one to get those in, yes? Okay, so I just want to make sure. Okay, so I'll start with the crystals there. So 2.3 and 3. I'd like everybody to do 2 dots, right? So you have 2 samples of size 3. I thought I had 2 from you earlier, Holly. So the 6 and the 2, did you just do like two rolls, 2 individual rolls? These are supposed to each be, oh, let's see. So, okay, so 2.6 and then 3.3. So maybe I wasn't super clear on that. So again, let me explain. So we're going to roll 3 dice. I always get the plural form of that word a little bit mixed up. But anyway, we're going to roll 3 dice, and we're going to add the 3 numbers up and divide by 3. Okay. Okay. Let's see here. Okay. Let me go back and just erase. So I put some in for you, Polly. Let me erase those so we don't get the bad ones in there. So yeah, let me take out that 2 and the 6 because that's what I had in for you. So what numbers did you get? What were your 3 numbers? So you can just kind of start from scratch there. So just roll 3 times, add it up and divide by 3. And then that'll be your first dot. So for example, here I'll do a couple more. Okay, so I'll go, and then I have my 3 numbers, right? I have a 6, a 1, and a 5. So that's 12 divided by 3 is 4. Okay, so no harm in having more dots here. So I'll just add in another dot there. Okay, great. So 3.66 and 3.33. Great. All right. Anybody else? So let me just confirm that. So somebody did get 2 1s in a row, right? Okay, so I'm looking at the numbers here for Killian. So you got a 1 and a 1. That's perfectly fine. It happens. So what are we seeing here? Well, what is the balancing point? If we were to try to balance this, if you were to imagine this is like a seesaw, where would the balance go? Well, you know, pretty much in the same place, right? Okay, maybe a little bit to the left, um, but yeah, about the same place, right? So what's going on here? As the sample size gets larger, the center stays the same, more or less, right? And it stays pretty much what we expect it to be, right? The actual parent population is at 3.5 for the average roll for the middle of the distribution, and the center here is about the same, okay? But what happens to the spread? Okay, with a smaller sample like this, it's not not like super clear the comparison here, but I think you can tell it is starting to get a little bit more compact here in the middle. Okay, so the spread, at least in theory, is supposed to get smaller. Okay, and that's exactly what we saw with our p-hat sampling distribution, right? The larger the sample size, the more compact, the less the standard deviation. And the same thing here. And finally, the shape becomes approximately normal. Okay, so this is the central limit theorem applied to sample means. Okay, and it's extremely important. It means we can now use the normal distribution to make predictions about um, X bar. Okay, good. So let's do some practice problems. Okay. Okay. So the center stays the same. So it's the same as the mean of the parent population. The spread gets smaller, and as the sample size gets larger, right? So if n is getting larger and it makes the standard deviation less, then it means that n is in the denominator. Okay. So we call this the standard deviation or the sampling error for the uh, for the sampling distribution for X bar. Okay. Now these formulas are on your formula card. Okay, so you don't need to memorize them. Wouldn't hurt, but you don't have to. They're right here. Okay, so it's the mean and the standard deviation of the sampling distribution of X bar. Remember in chapter 3, we had these, right? The mean and the standard deviation of the sampling distribution of P hat. Okay, so very similar idea, but instead of categorical data and P, we're working with quantitative data and mu. Okay, so instead of population proportions, we're now working with population means. Okay, all right, so with these formulas in place, let's do some problems. Okay, and they're here. We have directions here for GeoGebra. So let's jump right into a problem here and give this a try. So let's go back to data, maybe business analytics. Okay, so if you own a business, especially maybe like a larger business, you might have like a sophisticated kind of data collection and data analysis team. And Burger King, it's a huge company, right? So they're tracking quality control and customer volume, right? So these companies will have typically a drive-through, and then they'll also have an in-restaurant option. So they're of course they're very curious about how many people are going through each one, right? So we've got this data set. It tells us the number of number of cars arriving per hour is right skewed with an average of 20.4 cars per hour and a standard deviation of 5.7 cars per hour. Can you compute the probability that 22 or more cars arrive in a single hour? So where do we get started with this? Well, let's think about the distribution. Okay, so you've got a number of cars arriving per hour. Obviously, it's not the same every hour, right? There's going to be some sampling randomness going on, right? So some hours you'll have more cars, some hours you'll have fewer cars. You will have an average number, and it says that average is about 20.4 cars per hour. So every 3 minutes or so, you get a new car, but it's right skewed. Okay, so if we draw the right skew, it might look something like that, right? So the average is going to get pulled over a little bit from the mode. So maybe there's 20.4 cars per hour for our population mean. So this is the parent population, and it is not normal, okay? And since it's not normal, we can't really answer probability questions like this. Okay, so we're going to select one random hour and want to know what's the probability that the number of cars, which we could call X in that hour, is more than 22. Well, we don't know. We can't calculate it. No, we can't compute it because it's not a normal distribution. How do we know it's not normal? Because it's right skewed. Okay, so what does that mean? Well, we're stuck there if we're talking about one single hour, but if we use a sample of hours, let's say we take a random sample of 42 hours, then we might be able to use the central limit theorem to construct a normal sampling distribution. Okay? So what are the requirements? Well, there's two ways of getting a normal sampling distribution. Okay, the first way, I don't want to bounce around too much here. Let's see, this is on page 120. Let me use my second document here. So on page 120, we have the central limit theorem, right? There's two ways of getting a normal sampling distribution. Okay, either the underlying parent population is already normal, or we have a large enough sample. So how large is large? 30 is a good rule of thumb. So if you're having samples of size 30 or more, then the central limit theorem will kick in and the sampling distribution will be approximately normal. Okay, so is the parent population normal? No, it's right skewed. But it doesn't matter because the sample size is large. Okay, so we say since n equals 42 is more than 30, the central limit theorem guarantees that we'll have a normal distribution, or at least approximately normal. Okay, so the shape will be normal. What's the mean? Well, the mean is the same as the parent population. So it'll be mu, or 20.4 cars per hour. What about the spread? Well, the spread in the parent population is 5.7 cars per hour. But this is where things change a little bit, right? As we saw in our dice rolling applet exercise, the spread is reduced with the larger sample size. So as n goes up, the spread goes down. It's the same thing we saw in chapter 3 with p hat, right? The larger the sample, the smaller the standard error. Well, the same thing occurs here. The standard error for x bar is sigma divided by the square root of n. So sigma is 5.7, and we're going to divide that by the square root of 42. Okay, so pull out the calculator. We're going to go 5.7. We're going to divide that by square root of 42. Okay, so the standard deviation decreases quite a bit. It goes from 5.7 cars per hour down to 0.8795 cars per hour. So the standard deviation goes down quite a bit. It was about 6. Now it's way down under 1. Okay, so in other words, the sampling distribution will be normal. Let me draw that here. I'm going to line it up with our right skewed parent population. So the mean is still 20.4, but the spread is much less. The spread in this parent population was 5.7, right? So sigma was 5.7. Now the standard error for our sampling distribution is under 1. So what you want to imagine is this distribution is going to get like pinched in, right? It's going to be much narrower than the parent population. So if it gets narrower, then it has to get taller in the middle. Okay, so it becomes a symmetric normal distribution. So it'll be centered at the mean, and it will be a tighter, denser distribution. So this is the parent population. This is the sampling distribution. So what that graph on the bottom represents is all possible samples, all possible sample means from all the different possible samples of size 42. It's kind of a, weird idea to wrap your mind around, but we've already done it once in chapter 3, so it should be a lot easier here in chapter 4 to do that. It's simply all of the possible x bars when you're looking at samples of size 42. Why do we do that? Because we have to understand how x bar behaves, because we're going to use x bar for confidence intervals. and later hypothesis tests. Okay, so we can answer the question, what is the probability that a simple random sample of 42-hour time periods results in a mean of 22 or more cars? So we're going to take a sample, a random sample of 42 hours at this drive-through, and then each of those randomly selected hours, we're going to count the number of cars that go through. Okay, so if you have 42 counts, then you add them all up, you divide by 42, you get an X bar. So the question is, what's the probability that X bar is 22 or more? Up here, we couldn't answer that question, but down here we can, because we have a normal distribution now. Sampling distribution is normal, so we can answer that question. So let's do it. Okay, so we'll use GeoGebra. We'll use GeoGebra's normal probability calculator to do this. Okay, so we go over to GeoGebra, we put in our mean and our standard deviation, and it tells us what that probability is. So here we go. Okay, so we're going to open up GeoGebra. We're going to go to the probability calculator. We're going to go to distribution. We've already said that the mean is 20.4. The standard deviation, the standard error, 0.8795. Why do we call it the standard error? Well, what is X bar doing? It's estimating mu, right? So when X bar moves around, it misses mu a little bit, right? So that miss is called error. And so if the standard deviation is telling us how far X bar is from mu, then it's basically like an average or standard error, right? So that's where it gets its name. Okay, so we want to know the probability that X bar is 22 or more. So we're going to go greater than. We put in 22, and we see that that's pretty far up in the right end of the distribution. Okay, what's the probability? About 3%. So if you take 42 randomly selected hours and you count the number of cars that go through the drive-through in each of those hours, you add all of them up, divide by 42, you get an X bar. You get an average number of cars per hour in your sample. So the likelihood that average is more than 22, I don't know where that 5 came from, is 0.0344. Okay. All right. So sampling distributions, it's the first couple times you see it, it's sort of this strange theoretical abstraction, right? This collection of all possible samples of certain size. And at first it's kind of tough to work with, but you've already worked with it once in chapter 3. So it's the second time you've seen this in chapter 4. So I think it'll come together for you pretty quickly. I want you guys to try one. Okay. In the second exercise, we're looking at quality control again. So maybe we're back at the Coca-Cola factory plant, and they're making 12-ounce cans of soda, like lots of them, right? And so you can't measure every single can, right, after it's been made. So, they're using samples. So we can imagine that we're going to do a sample of, say, maybe 36 cans. So we'll do twice. We'll do once where we're just looking at a single can, and then once at maybe 36 cans. Okay, and so if the machine is running correctly, let's see, I had a question here. How did I get 0.8795? Great question. It's this formula right here. The standard error for X bar is the parent standard deviation. So it's the standard deviation of the parent population, and then we divide it by the square root of n. Why the square root of n? Well, as we saw, n is just sort of intuitively makes sense. The larger the sample size, the less the bounce, the less the standard error for X bar. So I took sigma and I divided it by the square root of n. Okay, sigma is this right here. It's this 5.7. So I went 5.7 divided by the square root of the sample size, which is 42. So let's do that on the calculator. So I'm going to go 5.7, and I'm going to divide that by 42 square root. There's our number right there. Does that make sense? Great. All right. So I want you guys to try one. And yeah, it's kind of tough, but just jump in and give it a try. So we've got this. So again, just imagine you're at the plant, you're a quality control engineer, and if the machine is running correctly, the average fill should be 12 ounces, and we're okay with some variation from that. 0.06 ounces, nobody, no like normal human can detect that difference, right? So, slight variation is fine. Now, if you start getting variations of, more like half an ounce or like an ounce, then that's problematic. But 0.06 is okay, right? So there's some level of variability you can live with, and that is 0.06 ounces. So what's the probability that a single can, so if we take a random sample of one can, what's the probability that it has less than 11.82 ounces in it? That's the first question. Then I want you to think about the sampling distribution for samples of size 36. Okay, so the first one is just a single can. You're going to look at that and answer a question about the fill. Then the second one is more like in the context of sampling. So, maybe every day or every hour you get a random sample of 36 cans, you open them all up, you measure very precisely the amount of soda, and then you make some inference about whether or not your machine is running correctly, kind of thing, right? Okay, so I'll be quiet for just a couple of minutes. We don't have a ton of minutes here. So, but I would like you to just practice with these ideas a little bit on your own before we move on. Okay, so let's draw a couple normal distributions. It says the parent population is already normal. So this is the distribution for single cans. The average is 12 ounces. Okay, let's see here. So for question one, let's see. Perfect. Yes, thank you, Laura. That's exactly right. Very nice. Okay, so the parent population, great. So it looks like you guys are doing great with this. Perfect for both of you guys. If it's already normal, then we can just go right to the normal distribution, right? So 11.82 is to the left of that, right? So maybe 11.82 is over here. So if we're less than that, that's the probability, right? So we're going to open up GeoGebra there. Perfect. Yep, you guys are right on there. So we'll open up GeoGebra. We'll put in the new mean and standard deviation. So it's 12, and then 0.06, okay, and then less than, less than 11.87. Sorry, 11.82. Okay, so yeah, it's very, very, very unlikely that you would get a can that has less than 11.82 ounces. Okay, so 11.82 ounces is probably undetectable anyway, right? If you got a can with 11.82 ounces in it, you probably wouldn't be able to even tell that that's underfilled, right? So I think they're fine with that kind of decision, right? I mean, even at that amount, which would be hard to detect, that's only like 1 can in 1,000 would have that little in it, right? So it's a very nice process here without a lot of variation in it, right? So that probability, it's not too hard to calculate. We can just go right to the probability calculator. 0.00135. So about 1 out of 1,000, 1 or 2 out of 1,000 cans will have that little in it. Okay. All right. A production manager takes a sample of 36 cans, right, to check the machine, right? Cans of Coke, it's not like a Ferrari or something, right? I mean, it's fairly inexpensive, so they can do larger samples and destroy 36 cans. It's not going to hurt them that much. So the mean will be the same as the mean of the parent population. Okay, so it'll still be centered at 12 ounces, and the shape will also be normal. If you're already drawing from a normal distribution, then the sampling distribution will be normal. But if you have 36 cans, it's very hard to get 36 extremely underfilled or extremely, overfilled cans, right? So that has an effect of sort of tamping down the tails of the distribution and pinching in the rest of the distribution, making it taller, right? So it's taller in the middle and it's narrower out on the sides like that. So it's still a normal distribution, but it's a tighter distribution, right? And we know the formula for it. It's sigma divided by the square root of n. Okay, so we take the parent population standard deviation, which is already very small, and we divide that by the square root of the sample size, 36. Why 36? Well, it's actually an easy number to work with. That becomes 6, which is 0.01. Okay, so yeah, 0.01 is less than 0.06, right? And that's reflected in this graph here being narrower than the one above it. So you take a sample of 36 cans, right? So you open all those 36, you carefully measure the fill. What's the likelihood that the average of those 36 is 12.2 or more? Okay, so 12.02 is just very, very, very slightly more than 12, right? 0.02 ounces, certainly that's beyond the ability of any human to detect just by looking and drinking, right? So the very, very slight deviation from 12. So how likely is it that you would get something that's deviating that much? Well, we know it's normal, so we can go to the normal. The standard deviation now is less. It's the standard error, 0.01. And so if we're going to be greater than 12.02, it is possible, but not very likely. So even a very slight, like, 0.02 ounce deviation from the mean or more is very unlikely, right? It's only about a 2% chance of happening. So go 0.0228. Okay, and believe it or not, this ability here is extremely important for us. This sampling distribution, the central limit theorem, allowing us to have sampling distributions that are normally distributed, is the foundation for how we build confidence intervals, and soon after that, do hypothesis tests for quantitative data. Okay, so all the fields out there, from biology to economics, political science, sociology, chemistry, all of these different fields that use quantitative data, they will typically use confidence intervals to make inferences about about the population. Okay, and it's all based on this idea right here. Okay, so this ability to make a probability statement about a sample is really quite amazing if you think about it in the right way. It's quite powerful. Okay, and we're out of time for today. We're a little bit behind schedule. We're not like terribly behind schedule, but just a couple pages behind schedule. It's not a big problem. We'll get caught up. But are there any questions as we break here for the week? We're done for this week. Fall break is next week, next Thursday. So we'll have class on Tuesday. We'll just steadily chip away here at chapter 4. No questions? Well, then have a good weekend, and we'll be back on Tuesday to continue on. I'm still working through grading those exams. I hope to have them in by tomorrow for you guys in Canvas. Okay, so have a good weekend. See you all on Tuesday. Take care. Thank you.